Hey everyone, I'm Travis Spivey, joined with my son,
Jordan Spivey, and if you're new to the channel, hit that subscribe button so you don't miss out on any of our awesome science videos. Also, scan the QR code in the top left corner of the screen to contact us and explore more of our awesome content and material.
In today's video, we will go over the first and second laws of thermodynamics and how they affect energy transfers throughout an ecosystem. So let's do this.
Our learning target for today is I can develop and use a model based on the laws of thermodynamics to predict energy transfers throughout an ecosystem.
The first law of thermodynamics deals with the total amount of energy in the universe, and in particular, it states that the total amount does not change. Basically, the first law of thermodynamics states that energy cannot be created or destroyed. It can only be changed or transformed from one form to another. This law may seem kind of abstract, but if we look at examples, we'll find that transfers and transformations of energy take place around us all the time. For example, light bulbs transform electrical energy into light energy or radiant energy. One pool ball hits another, transferring kinetic energy and making the second ball move. Plants convert the sunlight energy into chemical energy stored in organic molecules. You are transforming chemical energy from the lunch you ate into kinetic energy as you walk, breathe, and complete a workout after a busy day. It's important to know that none of these transfers is completely efficient. Instead, in each scenario, some of the starting energy is released as thermal or heat energy. When it's moving from one object to another, thermal energy is called by the more familiar name of heat. It's obvious that glowing light bulbs generate heat in addition to light, but moving pool balls do too thanks to friction, as do the inefficient chemical energy transfers of plant and animal metabolism. To see why this generation of heat is important, stay tuned for the second law of thermodynamics.
The second law of thermodynamics states that the entropy or disorder of an isolated system will always increase until it reaches a maximum value. That sounds so confusing, so let's hope it makes sense. At first glance, the first law of thermodynamics may seem like great news. If energy is never created or destroyed, that means that energy can just be recycled over and over again, right? Well, yes and no. Energy cannot be created or destroyed, but it can change from more useful forms into less useful forms of energy. As it turns out, in every real-world energy transfer or transformation, some amount of energy is converted to a form that is unusable, which basically means it is unavailable to do work. In most cases, this unusable energy is in the form of heat. Although heat can in fact do work under the right circumstances, it can never be turned into other work performing types of energy with 100% efficiency. So every time an energy transfer happens, some amount of useful energy will move from the useful to the useless category in the form of heat. Question: if energy cannot be created or destroyed and is transferred from one form to another, then why do they say we have an energy crisis? Pause the video and take 2 minutes to answer this challenging question. Now let's take a look at entropy and the second law of thermodynamics. The degree of randomness or disorder in a system is called as entropy. Since we know that every energy transfer results in the conversion of some energy to an unusable form such as heat, and since heat that does not work goes to increase the randomness of the universe, we can state a biology-relevant version of the second law of thermodynamics. Every energy transfer that takes place will increase the entropy of the universe and reduce the amount of usable energy available to do work. In other words, any process such as chemical reaction or set of connected reactions will proceed in a direction that increases the overall entropy of the universe because they release more and more unusable heat energy.
Now that we have some understanding about the laws of thermodynamics, let's talk about how they impact food chains, food webs, and trophic levels. Let's take a look at the following trophic levels model. We know that all energy begins with the sun and is transferred to plants. What you probably didn't notice is that the sun has 1 million kilocalories of energy, but the plant only took in 10,000 kilocalories of energy. This is because most of it is lost as heat energy by the plant. Notice that as we go up to the primary consumer level with the grasshopper, it only receives 1,000 kilocalories of plant energy. This means that it only receives 10% of energy from the plant and 90% is lost to heat energy. You will see the same pattern as we go up in trophic levels from the grasshopper to the mouse to the snake. Each organism only receives 10% of energy and there is a 90% loss at each trophic level. The 90% loss of energy is because organisms need metabolic heat energy to power bodily functions such as breathing, thinking, walking, communicating, and many other functions. The use of this energy for these different functions releases a large amount of heat energy from their body, 90% to be exact. The first law of thermodynamics is demonstrated in the diagram by showing that matter and energy is neither created nor destroyed, it's only transferred from one form to another. The matter and energy from the plant is constantly being transferred from one form to another as it passes up the trophic levels by the organisms eating one another for food and energy to power their life processes. Since organisms need energy to survive and power their life processes, they lose most of it as heat. Now this demonstrates the second law of thermodynamics, which states that the entropy or disorder of a system will always increase until it reaches a maximum point. Basically, as we move further up the trophic levels in the model, more and more energy was lost as metabolic heat to power bodily functions, which lead to more energy or disorder in the system. The more heat lost to the environment, the more entropy and or disorder in the system and universe as a whole.
And that's the video for today. Now let's test your knowledge to see how proficient you are with developing and using models based on the laws of thermodynamics to predict energy transfers throughout an ecosystem by taking our video quiz.
Use your electronic device to scan the QR code at the top right of the screen, or you can click the link in the description box below the video to take the quiz.
Remember, 80% or higher for proficiency. Record your results to your proficiency sheet, and if you don't get it the first time,
you better keep going because it's not over until you win. Don't forget to hit that subscribe button, click that bell icon, and also scan this QR code to contact us and explore more of our awesome content and material. Peace and have a positive, productive day.
Ugh.